Thank you all for coming. Today it is my really great pleasure and honor to have Professor Hasan here with us and share with us his insight about topological phases. And Professor Hasan is a professor at Princeton University, and so he is an expert in many things. So including strongly correlated systems, all sorts of novel superconductivity, high TC materials, and above all, is the leading experimental physicist in topological materials. So in the past decade, he has less than a decade, he has discovered many topological materials, starting from the first one probably was bismuth antimony, the first 3D topological insulator, and then the bismuth selenide bismuth telluride, and the topological crystalline insulator, topological superconductors, 3D in recent years, 3D Dirac materials, and Weyl semimetals. He discovered them all. So it just if you look at his publication list, you'll be absolutely amazed. So and what I found is what is even more shocking to me is that Professor Hasan got his PhD from Stanford University in only year 2002. That really surprised me. Only a few years before me. So, and I don't want to take too much time, so I will just give the rest of the time to Professor Hasan.
Thank you, Pete. It gives me a great pleasure to be visiting here. This is probably the most wonderful, most beautiful setting to have a workshop on. I'm sure all of you are enjoying, and I'm enjoying as well. Okay, so as Vic mentioned, I will talk about new topological states of matter, and I'll describe the term new. I mean, at what point, the time frame we're talking something new, and I guess most of us are physicists here, so this slide may be a bit unnecessary, but let me remind you that much of the classification of matter or particles or forces are based on broken symmetry-based classification. And maybe last 10, 20 years, we are also, as physicists, we're across the discipline, we're also thinking about topological classification of matter. And this is, of course, in particle physics through some string theories to topological field theories. In condensed matter physics, condensed matter systems, it's more exciting in the sense that we have realization of these topological systems, so we can play with them in the lab, and hopefully sooner or later we'll make use of them. So that's very exciting. So I'll start out with a brief introduction to topological physics in general, and mostly talk about experiments and with some new results. So here is, in some ways, the broad picture. So as when I took condensed matter physics, introductory condensed matter physics about 12 years ago, so I learned about states of matter, so like metals, insulators, magnets, and superconductors. If you think of Ashcroft Marmin or Kittle's book, so we learned about these basic states of matter. And what is exciting is that in last probably last 10 years or so, we have a topological version of all these things. We have topological insulators, we have magnets with some topological properties, we have, more recently, we have semimetals that have topological properties, and we have number of candidates that are possibly topological superconductors. So in other words, you can see that in last 10 years or so, we are entering a new era of condensed matter physics. We could call it some topological condensed matter physics. So it looks like finding these topological variants of the existing phases of matter is a very exciting direction the field is moving on. So as you know, that these topological classifications, these ideas, possibly, at least in condensed matter physics, it started with trying to understand quantum Hall effect, right? So quantum Hall effect, let me skip, I'll mention my team before I get to quantum Hall effect. So the experimental results I'll be presenting here is a collective effort of my students and postdocs, Suyang Zhu, Ilya Belopolsky, Nasser Ali Dost, Madhav Nguyen, Guang Bian, Hao Zheng. They form the core team, and of course we are closely working with the sample materials growth groups. The particular for the groups we are collaborating with for the results I'll be presenting here are Changlong Zhang, Shuang Jia, Ramon Shankar, Fengcheng Zhou, Taiwan, and we are also involved in growing some of these samples with these two, closely working with these two groups. And much of our experiments are carried out utilizing national lab facilities, although we have some facilities in-house. So much of the work I will present are the data are taken at the Advanced Light Source in Berkeley, SLS in Switzerland, and also SSRL at SLAC National Lab. Okay, so as I said, that at least in condensed matter physics, the topological thinking came in connection to experiments on quantum Hall effect or Hall effect, and so one can say that this is the first prototype of a topological insulating state in two-dimensional systems. So, so the quantum Hall effect, the surprising experimental fact about quantum Hall effect, as most of you know, is that why Hall conductivity is so precise. So traditionally, you would think in a relatively dirty sample, dirty crystal, you would not find such a precise property. You would not find such a precision level. So this is surprising that something is not depending on the details of the disorder potential in the crystal, the imperfections of the system. So what makes the system ignore that imperfection, right? So that is the key to understanding the precision of quantum Hall system. Was the first route to topological thinking in condensed matter. So the seminal paper by David Thouless and collaborators, they identified this the quantum of the quantum Hall effect as a topological quantum number, in the sense that it involves the Berry curvature in momentum space, and the integral goes over the occupied bulk bands. So although this quantum number, this topological quantum number, is giving me a measure of the boundary number of edge states, the boundary states in your system, it's directly it's defined by the bulk. So this bulk boundary correspondence, edge bulk or bulk boundary correspondence is the key to its topological protection. Unless you drive a phase transition in the bulk, this number of edge state is not going to change. So so as long as there is no phase transition in the bulk, the edge states are topologically protected. So of course this is known as the Chern number. So so the general message we get out of it is that the topological states have some sort of robust property, and experimentally it can lead to high degree of precision. So this is quite exciting from an experimental point of view. You want to find what other, you might ask what other properties we could look for in some random material that has that degree of robustness and this level of precision. So, so that is the general search for why we want to find topological states. So the quantum Hall state, as you can see, as you know, this integer quantum Hall state, it breaks time reversals. You have to apply a field, and it breaks time reversal. So one might ask, from experimental point of view, that you need a magnetic field. So this beautiful property of protected states, can we make use of them, or can we find them in systems without a bulky magnetic field? So that is a barrier in making devices, right? And can we also find that in higher temperature? So if you like, from experimental point of view, we want to find something that I can operate without a field and at higher temperature, at room temperature, right? So you could say, one could say that the theoretical search for finding a time reversal invariant topological state of matter is the right direction. You want to, from experimental or application point of view. So around 2004 and 5, Kane, Mealy, and a number of other theorists were thinking how to realize a time reversal invariant system that may have quantum Hall-like behavior. So the obvious way to think about it is, the simplest way to think about it is that think of a quantum Hall system, field up, spin up, field down, spin down, and think of their combination, and one can realize such a thing. Now it's time reversal invariant if you combine the two, but what is the real interaction in the solid that will create such a scenario? And this is where spin orbit comes in, because now you have a velocity dependent field. If the electron is moving this way, you could have, it will experience a field in the relativistic limit up, and then in the other direction it will. So you could, the spin orbit interaction could do the job. But now, to define the invariant, one can see that the Chern number paradigm is not working, because if you have a sample like this in this configuration, your Hall conductance is 0. The Hall conduction from the up channel is canceling the Hall conductance you get from the down channel. So this would tell you that this Chern number is 0, right? So that in the integer quantum Hall sense, this Chern number 0 would mean that you have no edge state. In the real sample sense, it would mean that these edge states you could think of them, but they're not robust, they're not protected. So then the challenge is there some other topological invariant that could still protect this type of helical edge channel? So this is not protected by the Chern number, so that's 0. So this is, I believe, this is the theoretical breakthrough in the field, that the realization that you could write down a different type of invariant, Z2 invariants, based on the parities of the block states. And in the inversion symmetry, if your crystal has inversion symmetry, then these invariants take a simpler form, and you could write them, the products of these parity eigenstates. And then since they're based on parities, so they're die-valued. You could have 0 or 1. So then when you have 0, you don't have that protection for those helical channels. And when you have 1, then you have those channels are protected. So those Kramer's pairs, it's describing their protection in this sense. So how does it translate to the bulk of the crystal? Right? Topology is about bulk boundary correspondence. The bulk of the crystal, so if this invariant is non-zero, then this is set by the condition when the number of bands, the number of band inversions in the bulk is odd. When you have odd number of band inversions in the bulk, it will, the helical pair will be protected on the boundary. So, and then one can also generalize that in 3D. In 3D, there are 4 such invariants, and one can try to construct a 3D state by stacking the 2D states. But then this is not necessarily if you just stack them in a conventional way. Well, I mean, if you just, just if you stack them linearly, then there's no guarantee the edge states in a real experimental sense. They're stacked. Then you have a surface state on the sides, right? But this is not guaranteeing a state on the top or the bottom, right? So this is not. So for that reason, it's not necessarily protected. But in 3D, now that we don't have a chosen direction. So one way to think about the non-trivial 3D state and the stacked 2D state is to make a comparison with the quantum Hall states. Like if you stack the integer quantum Hall states, then you get, on the sides, you get surface states. But nothing is guaranteeing that you'll have top and bottom. But in this case now, in the spin orbit case, now we don't need a magnetic field, so we're not choosing any direction. So it's possible by having odd number of band inversion in 3D, we'll have, it's possible to have surface states encompassing all sides of the sample. And this 3D state is non-trivial. There is no quantum Hall analog of that. So that is quite interesting. Okay, so now we know that in the integer or fractional quantum Hall case, the Hall conductivity, how do we measure these Chern numbers? One, the direct way to look. Find about the Chern numbers is or topological invariance. You just to read it off your transport data, but now the analogous topological invariants that protect those boundary states in the Z2 topological insulator case, they are not directly related to a conventional transport quantity that we would typically measure in a lab. So, and then there are many of them. There are 4 of them that will specify the state precisely. And of course, some of them, the first one is the strong topological invariant that will make sure that you have that non-trivial 3D state which has no analog in the quantum Hall case. So this invariant is tied to the magnetoelectric quantization. And if you look at the magnetoelectric response, then you will get the theta term. That's it's coming from the odd value of this the first invariant or the strong invariant. And of course, this is similar to the theta vacuum state people have considered in particle physics. However, this type of measurement is quite challenging, and it has not happened yet. We don't have samples that work in those geometries. And in addition to that, but even if that happens, it just gives you the strong invariant. How about these other invariants? So if you consider all 4 invariants, and this is a Z2 state, right? So then you'd expect 2 to the 4 in 16 distinct insulators in 3D, right? So one of them is trivial because that correspond to all the trivial values of this invariant 0, 0, 0, 0. So then we have at least in 3D we have at least 4 distinct topological 3D topological insulators. And so now the question is, can we find these 4 distinct classes of materials representing those states of matter? So now since, as I said, this magnitude electric quantization measurement is extremely challenging, but we can make use of a more detailed measurement to evaluate, get a feel for to evaluate these invariants, because they can be the consequence is that you'll have odd number of crossings on the surface, odd number of inversions in the bulk. So if you can image the bulk and find odd number of inversion, or if you image the boundary, you'll find odd number of crossing, and then you see that these two are in correspondence, so that would be a proof of topological state. And then by measuring different surfaces, you could evaluate this invariant. Right? So this is the approach we are taking. So in other words, we are trying to image the surface and the bulk and do a complete imaging, look at the electron's energy, momentum, and spin, so we can precisely measure how many times it crossed the Fermi level between a pair of Kramers points. So this would give us a complete spectrum of all the topological quantum numbers defined in the theory. Okay, so that is precisely what we are after. We have been doing that. So we want to image these electrons both on the surface and the bulk. So how do we do that? The surface part is straightforward. You know, angular result photo emission spectroscopy is surface sensitive because the electron escape depth is not very, it's short. It's depending on the energy of the beam, it's 5 to 10 angstrom typically. But if you can use a very high energy beam, like go to a kilovolt, not only you have better penetration depth into the sample for the photon, but the electron has a higher kinetic energy, so its escape depth is also larger, and one can go up to like 30 to 50 angstrom at that level. So the typical so other than that, the tuning the photon energy to gain a surface bulk contrast, the rest is not that different from a standard photoelectron spectroscopy you learn in quantum mechanics or some elementary books. So we have photon in, electron out, and then in the scattering process, the energy, we consider energy, momentum, and spin, angular momentum conservation. And these conservation laws allow us to connect the beam parameters to the electron dynamical parameters in the system. So end of the day, what we extract out of the data is an electron single part. It's a single particle information related to the single particle Green function, the first order spectral function. Okay, and the spin detection is done. I did not draw that here. Spin detection is done either through after selection of the energy emitted beam direction and measuring its energy. It's typically done either through a further scattering with a magnetized film or through a spin orbit target. Okay? So if we apply those ideas, it's a modern version of photoelectric effect on some of the spin orbit, heavy spin orbit materials like bismuth antimony or bismuth selenide, what do we typically see? So what do we typically see is that if you don't look at these two families, if you just take some bismuth material at random, say bismuth nitride or bismuth arsenide or any of that thing, you'll typically see a pair of Fermi surfaces, two circles. And these are the Rajpa states. So bismuth is a heavy spin orbit system. And then when you break the inversion symmetry on the surface, the bulk bands are, they're not, I mean, the bulk bands are degenerate. But when you break that inversion symmetry on the surface, you get a pair of Rashba bands. But in rare cases, in few cases, these are examples of that, where you see the only one circle, only one Fermi surface if you compare it with the experimental data in Rajba system. So now then if you look at the spin polarization by further analysis of the ejected beam, then you see that across the Fermi surface, for example, if K plus, if in this case, if you go to K plus direction and if you define this to be negative, then on the other side you have reversal of polarization. And then any cut you take in momentum space, you see that there is the K plus, if there is a time reversal symmetric relationship that K plus and K minus goes up and down. And this is, it does not matter for our purposes, it does not matter what, whether we measure the exact polarization, exact ground state polarization of the system or not, because we're interested in the relative polarization, K plus and K minus, to look at the topological effects. So you might worry about in RPES whether we are measuring the exact ground state of the spin configuration or not. Yes, that is a concern, but for the purposes of looking at the topological structure, that detail is not relevant. We only need to know the difference between K plus and K minus. And we do always see, no matter which cut we see that it's reversed. So, so these are tailored materials. So you can see tuned bismuth selenide. But if you look at the pristine materials, cleave them, typically Fermi level is in the conduction band. So you'll have to do something else, dope on the surface or tune it. Yeah. No, it's actually after detecting the electron, looking at its energy, then we go analyze it through another scattering. Say I have a film polarized up, or I have a spin orbit target. So we accelerate this electron to high energy so we can pick up in the Mott scattering channel. So it's like extrinsic spin Hall effect. We pick up the angle dependent in the relativistic cross section, the spin dependent channel, so we can further isolate that. Okay, and in our purposes, we don't, we are mostly interested in this relative polarization. So we are not always trying to claim that this is the ground state polarization. In the scattering process, there is some decoherence effect going on, but it's not related to the topological part of the story. Okay, so then if you do that at all across the gap, across the bulk band gap, you can either gate tune the material, or you can do chemical gating. Actually, in this case, we are doing chemical gating. Dope on the surface and see what happens to polarization. And let's say if you are around this energy, you see this clockwise spin texture. As you go through the degenerate point, this is the Dirac node, the polarization is reversing. So this is guaranteeing that across the gap, no matter where you place your chemical potential inside, as long as it's inside the gap, we always have a single polarized Fermi surface. In other words, this Fermi surface, of course, has a pi Berry phase compared to, let's say, Rashba, because you take a spin half object in momentum space, which is a parameter space, you take it around 360 degrees, so you pick up pi Berry phase. So the pi Berry phase is guaranteed all over the gap, anywhere in the gap, it's guaranteed. And then we can dope it further, raise the chemical potential up here, and this is what I was showing in the beginning. And then we can see that this is smoothly merging, tangentially merging to the conduction band. So in other words, this is the surface is completely gapless. No matter where you place your chemical potential, you get a pi Berry phase Fermi surface. Okay, so and then how do we know that the stuff, this linear crossing, the stuff is two-dimensional. It lives on the surface, and the other stuff is on the bulk. So the typical method we apply is that we look at the kz dependence. By changing the photon energy, we can also change the momentum perpendicular to the surface. So that allows us to make a contrast that what part of the spectral function is coming from the surface, what part is coming from the bulk. So the bulk band should, as we tune in the z direction momentum k sub z, then the bulk band will disperse in that direction. And then this Dirac band, it's non-dispersive in that direction. So that way we know that the stuff inside the gap is in the surface. The other way to do that, to detect, is from a low takeoff angle. If you come in with a photon beam like this, your surface is like that, you collect electrons from a low angle, low takeoff angle. So then that will give you further contrast on the surface. So by combining a number of these things, we confirm that what we see in the gap region, the spin textured part is from the surface, and the stuff outside is from the bulk of the. So then to summarize this part of the data, let's draw a cartoon that what we see is that no matter which cut we take, we see that K plus polarization down and K minus polarization up, and that's all we have on the surface, right? So in other words, we have half the degrees of freedom on the surface compared to a Rashba system, where if I were to draw the Rashba system, I'll have two more modes, right? So now you can see that the systems, all these materials are non-magnetic. So what this cartoon is telling us, this data is telling us, that if this electron packet moving to the right, it cannot scatter back because there is no state available there. Actually, it's better seen here. So if you follow this track, then this entire line, these are all spin-up states, and these are all down state. So if you want to take a U-turn, then there is no state available there. So in other words, if you have a Fermi surface like that, your backscattering is forbidden. So there is no U-turn. So in principle, this should lead to non-dissipative transport, right? Okay, so in 3D, now we have to consider other cuts. So this is, I just considered one cut. I can consider other cuts. Now, one can see that this backscattering, non-backscattering is valid for any cut, but it can also, in 3D it can also do a side scattering. Non-180-degree scattering is allowed. And what else is interesting here is that there is a similar surface state on the side surfaces. And not only that, on the edge, the structure, the states on the edge is non-universal. It depends how states on these two surfaces connect to each other. And this is different from the 2D case. In the 2D case, it would be just like that, right? Okay, so clearly, in these systems, the surface electrons are spin momentum locked. And then, in this sense, they're helical. They're helical Dirac fermions. Okay, so helical Dirac fermion is the boundary signature of Z2 topological order. And so I promised that how do you get the topological invariant? You look at this Berry phase and divide it by pi, that gives you 1. So that means the first invariant here is 1. Okay? So now the next thing is, okay, so in what I have shown so far, in certain materials you get this funny surface state. And but how do I make a connection? How do I make a connection to the insulator that we all understand, the block band insulator that's something we learn in the textbook, right? So what is the, or is there a distinction between this insulator with funny surface state in terms of can we start with a block band insulator and evolve the insulator into the other insulator that has this funny surface state with or without quantum phase transition, so that will define whether we really have a distinct new state of matter or not, right? So in order to do that, what we did here, we're looking at some analog of that bismuth selenide. It's a bit more complex. It has thallium in there, but the advantage here is that we can continuously change the ratio of sulfur to selenium content from 0 to 1. And why do we want to do that? Sulfur is a lighter atom and selenium is heavy, right? So then selenium has more spin orbit and sulfur has less spin orbit. So what we want to see, if we reduce spin orbit effective spin orbit coupling in the system, can we recover my good old insulator, right? Do I have to go through a phase transition on the way? So that's the idea. So we start with, on this end, this is the analog of bismuth selenide, and we can see clear, it's just like the data I showed in the last slide. We can clearly see a surface state, and we can see the bulk bands, there's the indirect gap, and then the spin polarization, this spin texture is there, and it's gapless in the surface. So as we lower spin orbit coupling, in other words, increase sulfur content in the system, then at some point we see that when we have all sulfur, so we are in the lowest possible Z range, then we see that now I see a valence band and a conduction band, but the band gap, there's nothing in the band gap. In other words, if I lower the chemical potential here, I could make the surface insulating, right? So this is a bulk insulator with insulating surface. So now we can see some trend in the data that the conduction band is lowering energy, and valence band, apart from a shift in the chemical potential, global chemical potential of the surface, we can see there is a rise of the valence band. This is probably better here. So we can see that there is a direct gap in the system, and the spin polarization is, there's no net polarization. There's no texture on this type of Fermi surface, I mean on the band like that. So this is conduction band, and then as we increase spin orbit, this band gap is closing, and when it closes the gap, only then we start to see past that closing. 0.6 is here. I did not mark that, but this is 0.6. When we have closed the gap, then the surface states are born there. So in other words, there is a clear distinction. One has to go through a phase transition. There's a phase transition between a trivial insulator, block band insulator, and a topological insulator. And we can see the clear correspondence that the surface states they only appear in the band inverted regime. So if you like, this is another evidence of bulk boundary correspondence. When a phase transition has happened in the bulk, and the odd number of band inversion has happened, only then we have the surface state. So this gave us, yeah. Yes, precisely. In this paper, we actually argued that there is a 3D Dirac, right? So in this case, precisely at the 3D Dirac, at the phase transition point, we could see that all the bands are now dispersing in all momentum space direction, and they're dispersing linearly. So right at the phase transition, we have a 3D Dirac state, and this is the true analog it's the analog of graphene, the higher 3D analog of graphene. In this paper, we actually talked about that. Now, this is what I'm getting to. Now, so what I just showed, that imaging a topological insulator being born out of a block insulator as spin orbit interaction is tuned. And as Vic is saying that in this system, we already have a 3D Dirac at the phase transition. Now, I think what he has in mind, why don't you magnetize the system or break the inversion symmetry, then you'll get Weyl. And in fact, precisely that is what we did to find the Weyl semimetal. I'll make this connection, and that gave us the material algorithm how to get to that. Okay, before I get to that, let me tell you a little bit about the transport results on these samples. Now, pure bismuth selenide, it's hard to make clean enough to be truly insulating in the bulk, but if you mix bismuth selenide and telluride in some magic proportion, chemists have all figured that out, and put some antimony in there, then you could make it, so you can make the chemical potential stay within the gap, band gap, even under the ambient condition. The data I showed, the tailored samples, they are insulating only in UHV, but this bismuth, antimony, telluride, sulfide, these samples, their chemical potential stays inside the gap even if you take it out of UHV. It just stays there in air. So then you can do transport measurements. These measurements are done by Young Chen at Purdue. We did the RPES for these samples. And what is seen in the data that this is the measurement geometry. If you can clearly see these integer quantum Hall steps in this system, and then these are all integer as expected, because in a topological insulator case you have signal for the transport. You have signal from top and bottom surfaces, so this half should add up to 1. So you'll only see the integer thing. But then what is interesting is that you cannot see a quantum Hall signal if the bulk is not insulating, right? So what we are saying is that although this is definitely signal from the surface, but this is also giving us a measure how insulating the bulk is, right? So this is a way we can test how insulating the topological insulator is. So to summarize, the data so far and make a contrast between 2D and 3D is that in 2D, in the integer quantum Hall case, you have a chiral edge mode, and it's described by one invariant. That's the Chern number, and this is the Chern parity or Z2 invariant. When you have you consider 2 copies of that, you make it a time reversal invariant. You add another pair, so the edge is not chiral anymore. Now it's helical. And in the 3D case, it's described by 4 invariants, and you have 16 topological states, and then they all depend on how these states connect on these surfaces, right? So and as I said, that if you have states on all surfaces, then you cannot start with an integer quantum Hall like state and get a topological states where all surfaces are gapless. So in this sense, it is this 3D strong topological insulator is a new state of matter. Okay, so I did not get into that, but some of these materials have very large gap, so you can see these states survive up to the room temperature, which is promising that no gap has opened in the system and the spin polarization has not decreased significantly. And you could see the absence of backscattering by looking at the spin texture or transport. So what is new is that these are not only just, they are described by new topological invariants, they have some very interesting, promising, their properties are very interesting and promising for future development of certain types of devices. Okay, so what is beyond topological insulator? Or one of the reasons to me why they're interesting is because you could tailor them in certain ways and get to other topological states of matter. For example, you could induce proximity effect and generate a topological superconductor, or you could dope the topological insulator, and if the parameters are right, you could get a topological superconductor just by doping the topological insulator. And the key to that is to realize helical pairing. And on the other hand, you could also try to close the gap in a topological insulator and realize other topological objects. You could realize a Dirac semimetal or Weyl semimetal, and they have both they have interesting states both on the surface and in the bulk. And this is what we'll talk about both. And then not only that, in the Weyl semimetal case, you could go further because these are metals, and then you could dope them and you could induce superconductivity in the bulk. So that will give you a superconductivity in a Weyl system. And under certain conditions, you could also find a topological superconductor out of a Weyl semimetal. And you could call them Weyl superconductors if you like, but there are different definitions of Weyl superconductors. But Weyl semimetals could work as a new platform for new type of topological superconductivity. There are different classes of topological superconductors. So this is very, very exciting. And then these Weyl fermions lead to different types of Majorana. Okay? So the basic Majorana platform is realization, what I just showed in the data, that K plus spin up, K minus spin down. If you have a Dirac gas like that, then you have half the degrees of freedom on the surface. If you like, you can call it's a half Dirac gas system. So in a half Dirac gas system, one can look at the BDG Hamiltonian, and it has a highly non-trivial ground state. It is a half Dirac gas superconductor is topological in terms of the BDG classification, right? So the one way to see that non-triviality is to look at the superconducting order. For example, you do that when you create a vortex and look at the contrast between the vortex, which is like the normal part of the superconductor, and the superconductor itself. And just as in the topological insulator case, the normal part and the topological insulator part, at the interface you have a gapless, you have a protected fermion. In this superconductor case, you also have a protected fermion, and that takes the Majorana form. Right? Okay, so the basic idea here is that in this Foucault proposal, you take this Dirac state and induce Cooper pairing, and you have half of that thing, and then this half Cooper paired gas superconductor is non-trivial. So let me show you some results how to realize that with a microscopic tailoring of this material. So we know that this bismuth-based materials have a single Dirac cone, and now if we grow that on top of a, say, S-wave superconductor, then we'll have some state at the interface where the superconductor and the insulator meets, right? So now the challenge is that how to figure out how to image what is going on at that interface, or if your film, TI film is thin enough, what happens on the top surface? The proximity may rise up to the top surface. So this is what we are trying to do here. We are trying to use ARPES to spectroscopically resolve the proximity effect, so that we know what is the microscopic Hamiltonian of that interface or the proximatized surface. So this is data from this type of interface. You can see that because of momentum resolution, we can isolate where the Dirac cone is, and then if we fix our momentum at the Dirac cone, and then look at the low temperature and see whether there is these Dirac electrons at the interface are pairing or not. If they're pairing, there will be gap, of course, and we can see some signature. And then how do you know that the gap we see at low temperature is actually related to the superconducting proximity or superconducting transition? When we raise temperature, we see that the gap disappears as you enter the normal. So these are some of the earliest data. Now we have better data on that. Now let's say if we look at a 4 nanometer film where the substrate TC is about 7 Kelvin, and we look at the region where the Dirac surface state should be, and then go down to start out with, let's say, 12 Kelvin or 7 Kelvin, we can see a Fermi step there. No obvious gap, but as we go down to 1 Kelvin, this is 6 Kelvin below the substrate TC, we can see there's a gap opening and a coherence peak developing. So nice thing about RPES is that we can select, we can look at the momentum, look at it in a momentum selective way. So what we can confirm that in these films, there is at least the surface states are definitely Cooper pairing because I'm just looking at the surface state part of it. And then we can see that the pairing disappears certainly above the substrate TC. By 7 Kelvin, we don't have the pairing gap. Then we can also, because of momentum resolution, we can also look at the K dependence, momentum dependence of the gap. If we look at much of the allowed direction within the experimental geometry, we don't see any signature of a node. So this is good. So this is consistent with, this is node-less superconductivity, and this is consistent with its topological signature. Now, we can also create a contrast because most of the sample, your Fermi level is not here. Your Fermi level is up there at the interface or in the top surface. Then you can see that there is proximity effect also on the bulk band that crosses the Fermi level. The surface band is on the edge. So we can lower the Fermi level here and look at it. And then we can, but I like to look at this one because I want to see if there is a difference between the proximity effect on the bulk band and proximity effect on the surface band, whether there is any spectral signature of that. So what we see that consistently that whenever we focus on the bulk part of the proximity gap on the bulk part of it, it looks like it deviates. I did not have that data. Let me see. Back. Oh, here. These both are surfaces. Okay, I can talk about the surfaces part. So what we see is that the bulk part has better fit with the S wave, whereas the surface part has better fit with P plus IP type of thing. But although this is consistent, but this is of course does not necessarily prove that you have the P plus IP type of state. But what it allows us to do next is that we can use this spectroscopic signature as a feedback loop on the growth method and optimize the surface part. In other words, how to get chemical potential down here and keep it stable, and then that will give us an optimization, material optimization algorithm where we can maximize the helical Cooper pairing channel. And then these samples are grown in a chamber that's connected to STM. So then we can also transfer, once we optimize that thing, that growth condition, then we can transfer that to STM chamber and apply a field and look at what happens at the vortex. The advantage here is that we also know what is a bad sample, what is a good sample, and we can study both with STM and the field, we can study both the bad sample and the good sample, make a contrast which zero bias peak is real or not. So this is work underway. You have some sort of unusual critical exponent, and these authors argue that this is some sort of supersymmetric critical point. So their argument is that if we tune chemical potential at the Dirac point, at that critical point, then the fermion velocity and the boson velocity, collective mode velocity, would be similar. So it turns out that we can dope manganese with a few % of manganese, and the surface doping, we can actually get to that critical point. So this is another interesting direction we are pursuing. And whether this theory is robust for the actual materials or not, we don't know yet, but it is, nevertheless, it's interesting to figure out what happens at the critical point between a helical topological superconductor and the Dirac metal. So that can be experimentally answered. So these two examples I gave, topological insulator and topological helical superconductor, in both cases, the ground state is gapped. In the insulator, we have the band gap. In the superconductor case, we have 2 delta superconducting gap, right? So the topological classification, that bulk boundary idea, it conceptually works out nicely. In the topological insulator case, if I close the gap, then the surface electrons, in the topological insulator case, the surface electrons are confined on the surface because there is an energy barrier into the bulk. So that bulk boundary correspondence is robust. But if we close the gap, then the electron has no barrier to enter the bulk, so then that the surface state is not well defined. Similarly, in the superconductor, if I close the gap, then there's the surface mode is not confined on the surface. So this is the conceptual challenge. How can we get a topological metal, right? So there is one, in my view, algorithm that I can make connection to. Now this goes back to Vic's question, that if you look at the topological phase transition in a topological insulator I showed earlier, you start with a trivial insulator, no gap, then you invert the bands, and then in the topological insulator case, you have indirect gap, you have surface states, but right at the Dirac point, it's a 3D Dirac point, right? Now the question is, can we get a similar 3D Dirac point in the inverted regime? It's certainly possible in this scenario. Here it is, that you go into the inverted regime, you don't open a gap by some crystal symmetry. There may be some crystalline symmetry that will protect these crossings. It's not forbidden. There are 230 space groups in the crystals, right? So in certain crystals, it will happen. You're in the inverted regime, but you have the Dirac crossing, 3D Dirac crossing protected. So then what could happen, that you could have a pair of arcs connecting these two crossings. Now, whether you will have that or not will depend on a number of different conditions, but one can think of it along this line, that if your chemical potential is here, you have a topological insulator, you have this surface state. Now imagine closing the gap. You could close the gap at 1 point or 2 points in the momentum space. If you close it at 2 points like here, then these 2 points you have a 3D Dirac cone in those points, but then rest of the surface states will look much like the topological surface states. Now the question is, are these surface states protected? Because if you remember the theory part in the beginning, that I argued that the topological surface states, according to theory, they're protected by those Z2 invariants, right? And Z2 invariants are defined only in a gap system, right? So now the question is, experimentally, will we see these surface states? Are these surface states robust in any sense? Because now this is the gap has closed. Yeah. Non-topological semimetal. In the inverted regime, if this is like this, you'll get a surface state. You mean with some sort of surface states, right? I mean, of course, there are trivial semimetals, but I'm saying that whether they have double surface states or not, I haven't seen any examples of that. I mean, if it is trivial semimetal, then you could have a double surface state, right? So that's next slide. So what I'm saying is that in a topological semimetal case, if the scenario is like this, the inversion has happened, these crossings are protected, the gap is closed. If these surface states are these surface states protected? So experimentally, we find evidence for that. In fact, in this is again a bismuth-based compound where the spin orbit comes from bismuth, and when you, it's in the vicinity of a topological insulator transition, and then you can see this. Deep in the energy axis, you can see that they're Dirac-like. So they can be thought of double Weyl type of thing. And then we do see these surface states protected. I'll come back to that point more in terms of the experimental data. So let me clarify the algorithm. So this is the critical idea, at least in my case. So you start with a topological insulator. It looks like bismuth selenide, Fermi level inside the gap. So it will be like that. Then I said that we can close the gap at 2 points. And these points would be, because this is at the critical point of topological and trivial state, these points would be the points where the bands are just inverting, and they will be 3D Dirac-like, right? Now, how to get a Weyl out of that is quite simple. You just break one of the symmetries, either break time reversal or inversion symmetry. In our case, we actually tried breaking inversion symmetry. So then we could split the Dirac into Weyl, and then you could connect it to the other end in the sense that you could again recombine them here. So in other words, these three ideas gave us an algorithm where in the material space to search for such a thing. So you want to search for a spin orbit material which has a spin orbit strong enough, which has the bands have inverted, but then in the physical property it's not insulating, it's metallic or semi-metallic, right? And then of course we want to search for something that has broken inversion symmetry. And so by searching, let me get to the search part. So then if you go to the material database, you find a whole lot of these compounds. But it turns out a whole lot of them are not single crystals. Nobody has succeeded in growing single crystals. They're just there. They're polycrystal. So it turns out that only a fewer crystals actually would work with real experiments, at least ARPES experiments. So then you isolate them, then the list becomes much shorter. And the other thing is that when you search with this, you don't know whether those your Fermi level would be close to the crossing, because you could have Weyl points all over the Briand zone, but that is not a Weyl semimetal. For example, iron has like hundreds of Weyl points in the so that question has to be answered experimentally. So you could predict a lot of Weyl crystal, and that is what was happening since, I think, 2010 or 11. Many theory group has predicted so many Weyl metals, but nothing came out real until the experimental work went on came into the picture. So the idea is to find a material whose natural Fermi level is close to some Weyl points, and now I give you a contrast that, for example, in the database, if you look at the tantalum arsenide, there are other compounds like these silver selenide and these other tellurides. From a theorist point of view, they all should be Weyl. So now you might wonder why what happens in reality. In reality, if you actually do experiments on these materials, we actually did work with these things, these other materials, they don't actually work. Either the Fermi level is way off, or they are not in the phase. They don't grow in the phase that has the Weyl at the near the Fermi level. So for that reason, the theoretical prediction alone cannot give you an experimental realization until you do these experiments. And these are the considerations that led us to discover this compound as a experimentally realizable Weyl. As I said, that by the theoretical argument, you could also say the reasons this should be Weyl, these all should be Weyl, but if you do experiments, they're not there. So if you do, then the calculation guides you in a different way. It helps you to find where to look for these unusual Fermi arcs. So let me go back a little bit, review the theory briefly. The Weyl particles are, of course, it started with Weyl, and then before the Higgs phenomena happened in early universe, in particle physics, all the particles were massless, and then the Higgs gave mass, Higgs electroweak symmetry was broken, and then the Higgs gave mass, and then all the particles, fermions, have mass now. So Weyl fermion existed before we all existed. So in early universe, there are Weyl fermions, and people like, say, Volovic and others, they have considered their topological properties in a Nielsen, Ninomiya, chiral anomaly, and all these things were considered. They were all even in the textbooks. So then one way to think of these unusual, these diabolical points or non-degenerate bands crossing, accidental crossing, is if in a very curvature sense, these are like monopoles. These are like extreme points in the very curvature in momentum space. So you have with definite chirality, and you can clearly define topological invariants associated with that. But what got us interested in this topic is what happens when these Weyl points are projected on the surface, because I can do surface measurements much easily. So, in fact, Ashvin is the one who pointed me to some of these papers where they predicted that when you project these Weyl points on the surface, you get a Fermi surface that looks fractional. In 2D, it looks like it has only part of it. And this is very, very unusual, very, very strange, because I have been measuring Fermi surfaces for many, many years, and I have never seen a Fermi surface in any sample that is not closing in 2D. So this is very, very unusual. And what is interesting is that compared to what particle physicists have considered regarding Weyl, in condensed matter, we also have this Fermi arc as some sort of emergent topological property. And then this Fermi arc is also topologically protected. So in these samples, not only the bulk is interesting, where you have chiral anomaly, you could also tune the Fermi level to the Weyl point, so then you'll get, your transport would be dominating from the Fermi arc. So the surface transport is also interesting. So this is very, very exciting. And so let me get to the particular geometry. In this particular class of compounds, you have 24 Weyl nodes, and they are close to the Fermi level. So this is the remarkable thing, which is hard to settle from experiments alone, from theory alone. So what happens is that if you take in these two mirror planes, the Weyl points are, they project. This is the distribution of these crossings, and then they project. If you project them on this surface, then these Weyl points project on the same point. although they're separated in kz. So it's, and then these W1 point projects are near the zone boundary. So then you have this distribution of projection of Weyl points on the surface of interest where you could do experiments on. And then, so what happens, so if we use low photon energy, which would be surface sensitive, then we see, we take a map, electron distribution map on this surface, momentum resolve, of course. We see a large blob of intensity here around the zone boundaries, and then we can see as you approach the zone center, we see these unusual shapes of these Fermi surfaces. It looks like there are two of those, and they sort of merge into one. And these things happen near the W2 Weyl point. Okay. So then we can take a close look at these things, and if we go, let's say, from gamma x direction, we can see that these this pair, they sort of terminate better than the gamma y point, and if we look close to the x point, we have this blob of things. So it's hard to, within our experimental resolution or anybody's resolution, it's hard to resolve them, but you would expect, based on calculation, you would expect that there is a trivial Fermi surface. I may have, can I borrow a pointer somewhere? Okay, good. So then, so it's hard to resolve this part. Let me go back. Hard to resolve how many Fermi surfaces are there, but you could say that there should be at least two, and it looks like they may be emerging from these Weyl points, this W1 Weyl points I showed, and then there is something in between, and but we could possibly focus on the gamma x direction where the data is clear, right? If we focus on the gamma x direction, we want to see how these pieces of Fermi surface propagate as we shift the energy, go to higher binding energy or come to lower binding energy. So we can trace them in the E versus K plot and see how the gap, I mean the difference between the band energies are shifting. So then we can see that these their dispersion behavior is as if they're co-propagating momentum space. And then here in this gamma y cut, we don't see much emerging from that point. So this is a bit unusual in the sense that you look like, if you want to believe that this is a closed Fermi surface, then it would look like there is some extreme point here, and then it's forming a loop. But then it's not a high symmetry point in the crystal. It's somewhere in the middle of the Briand zone. If it would be near some high symmetry point, it could have some other origin. Now let's see what happens to the bulk. So that's the phenomenological story of the surface state dispersion. Now let's see what happens in the bulk. So now what we do, we go to high photon energy, 650 eV. Now we're imaging more from the bulk, about 20, 30 angstrom from the bulk. And now we can see that I'm looking at the same part of the Briand zone. Now what we see is that we see Fermi surface, here the Fermi surface looks like 2 points. Those arc-shaped things, stuff is gone. And then these points are there on all directions, consistent with the symmetry of the crystal. So from a bulk point of view, it looks like this is a semi-metal with point Fermi surface, 3-dimensional point Fermi surface, and these points, these Fermi surfaces are also dispersive. Now let's make a contrast with the surface. When you go to lower photon energy, 60 eV, we see that these double arc type Fermi surfaces appear, and it's not clear whether those points are there or not. So this is clearly in contrast, and in between they evolve. In other words, this is really going from surface to bulk. And the way they evolve is that you can see directly from here that in the bulk you develop a pair of Fermi points in 3D, and on the surface you see a Fermi arc. So now the question is, do they match? In other words, these disjoint Fermi arcs, do they coincide? Do they terminate at the bulk Fermi surface, point Fermi surface? So in order to do that, we look at more 3D, the detailed dispersion of the 3D. For example, those bulk Fermi surfaces, those Fermi points, if we look at their energy momentum relation, we see like a pair of Dirac bands. They're shifted, and they're shifted in momentum space, of course, and then that leads to a shift in the energy space. And then these are so these are those pairs where they connect. And then and near the point, they're quite linear. And now, if we want to make a connection, so what we see is that these points are there away from the Kramers point or some rotational axis. So if you restore the crystal symmetry, if you restore the center of symmetry, then they would merge into a single point. So clearly these points are related to the inversion breaking of the crystal. So finally, what happens if we take the low energy data, the surface data, and superimpose that with the bulk? What we see is that indeed these point Fermi surfaces of the 3D crystal, they coincide with where the arcs terminate. So clearly the arc is non-closed on this surface, and that is where the bulk points are. So now clearly we see that there is a correspondence between the bulk band structure and the surface band structure, in the sense that there are non-closed arcs. They terminated where the Weyl points project. Okay, so this is the bulk boundary correspondence, if you like, that they're related to the topology of the system. So one can also think of further proof that, okay, so if these arcs are really arcs and they're related to the topological order of the system, then they should be non-degenerate in spin space as well, right? So the spin measurements confirm that these surface states are singly degenerate, and they have a very high polarization. In fact, I don't know of any topological insulator surface state with such a large polarization. So these results are further detailed in these papers, and they're further confirmed in a number of related compounds. And I should also say that there is Weyl physics also realized in photonic crystals as well by a group at MIT, and in these photonic crystals they can with diffraction experiments they can resolve these Weyl points, and but I think it's at this point it's a bit challenging to resolve the arcs, Fermi arcs, the surface states on the photonic crystals. So and then there is a group from IOP. They're also their first paper is on the Fermi arc, and then subsequently they have also looked at the bulk band structure and the surface bulk correspondence. And by now there are many more papers on this topic. Okay. So this is so all the stories so far on this class of materials are from ARPES or spin ARPES. So is there some other technique that is finding similar evidence? And of course, you think that STM would be ideal to look at least the Fermi arc part of it. And such work is beginning to happen. We are working on it. A number of other groups are working on it. And we do see these surface states on these materials. And not only that, if there is this Weyl point and Fermi arc correspondence in these crystals, there should also be chiral anomaly, the E dot B effect in these crystals, that those measurements are also beginning to happen. I'm sure it would be necessary to do far more detailed systematics to sort out the chiral anomaly contribution in these crystals, because here we also have trivial surface states and the band structure is complicated. Similar results have been reported in Dirac materials as well. Okay, so why these Weyl materials are interesting? What is the future like? As I said, one possibility we are pursuing is, can we grow these materials on top of a superconductor, like the helical superconductor, the proximity effect results I showed. Similar experiments can be done on these Weyl materials, and it would be interesting to find out what type of superconductor is realized on the Fermi arcs. Right? We have a pair of Fermi arc, but they are now disjoint. So what type of superconductor that would create? It's outside the Foucault type of thing, right? In the Foucault, you have a closed Fermi surface at the interface. And then we could also dope the bulk and realize superconductivity more easily than the topological insulators. Even topological insulators, people have succeeded in doping the bulk and realize superconductivity. But here, the advantage with Weyl is that they're metallic, semi-metallic. So you could dope to some extent and still maintain the topological character. So the superconductivity is accessible. In addition to that, as I said, that the Fermi arc transport is interesting. What is the surface transport? Because then you have top and bottom. In the presence of a field, the electron has to close the orbit by covering top and bottom surface, because half of the Fermi surface is in the bottom surface, right? And there should be there's theoretical proposals of photon-driven anomalous Hall effect, like if you come in with polarized photon, circularly polarized light, you could create interesting topological states. So I think I would say in general, unlike topological insulators where bulk was not so interesting, but it was a bit annoying, only surface transport was interesting. With the Weyl physics, you have interesting bulk physics and interesting surface physics. And by now, there are at least 8 materials that have been declared Weyl. So I think there is a very exciting time ahead. And you could always ask similar questions. The questions we asked in topological insulator: what happens if you magnetically dope it, you strain it, you nanostructure it, and all sorts of things. So I think there is a very exciting time ahead for Weyl-type physics. But in general, what is the pattern we see in topological states of matter? As I said, that in the beginning we had insulator, metal, magnet, superconductor. Now we have realizations, or beginning to have realization of all these things. So all of this is taking us to the new frontier of condensed physics, and that's topological condensed matter. Thank you.
Well, let's take the earliest one, the topological insulator first. The surface states are protected. How well are they protected? My question is, surfaces, you have to be rough. It can be, if you have a interface, you could have interatomic diffusion and all these sort of things.
Mm-hmm.
So,
yeah.
how well it is protected?
Right. The Z2 topological insulator, or say bismuth selenide, it's protected against, I mean, as long as time reversal symmetry is there. If you have magnetic impurities or magnetic field and all of that, then you'd see that, let's think about magnetic impurity, then your backscattering is now allowed, right? It can exchange, it can flip the spin, exchange the angular momentum. So it's protected against, I mean, as long as its time reversal symmetry is there, it should be protected. And then you could also ask, what is the experimental degree of protection, right? In fact, I find even the Rashba states are fairly strongly protected. It's very difficult to get rid of the Rashba states, although there is no topological mechanism protecting it. But in terms of experiments, you could do all sorts of wonderful things where the Rashba states are very robust.
Okay, so for your Weyl semimetal metal, so one of them is this niobium arsenide.
Right.
So any superconducting.
Right. This is a very interesting possibility. One could try to grow it on niobium selenide and induce the proximity effect there. Yes, I mean, we're considering that. But what is interesting, we don't know yet. I haven't seen any rigorous theoretical paper. What type of superconductivity would be realized on those arcs, right? Or would it be topological, or I don't know. I mean, there has to be some sort of classification. Yeah, I think there's room for theoretical work there. Yeah. But experimentally, it's feasible. We're actually already trying that. It's a natural thing for us to go for on niobium selenide. The data I showed, we put bismuth selenide. Now we just put niobium arsenide. So, yeah.
Many of the questions that you have addressed in your talk are considered also by the community of cold atom physicists. Now, so my question is, how do you judge, what is your feeling about the future development in this area, which can find interdisciplinary, let's say, connections
Oh, you mean
between
in the
solid
cold
state
atom?
and the cold atom community?
I see. Well, I mean, we don't have, we certainly don't have continuous tunability of these systems, right? We cannot continuously tune from, let's say, through the phase transition that creates these things. I mean, the Weyl semimetal, in some way, it's like a critical state where you are at the critical point. But it would be interesting to consider the continuous tunability and also dimensional crossover. You can start with a Weyl semimetal, and low D you could get a quantum anomalous Hall state in 2D. There is no Weyl state in 2D. It's a purely 3D thing. So I believe with the present material science and technology, it's not easy to reach those limits. But I don't know how interesting those states are in cold atom community. Or bringing in interaction physics there.
So my question is, everything so far seems very fundamental. So you are demonstrating on the topological character of the states.
Yes.
So when do you think this could be applied for something practical, or what could be the important applications that this?
Right. So one way to think about it is that one can. So what is the roadmap in the Weyl field? The roadmap in the Weyl field is that now we have Weyl semimetals with a very complex Fermi arcs, right? We want to find the hydrogen atom version of it. We went through that roadmap with topological insulators. In the beginning, the first topological insulator, we had 5 surface states, and then we figured out how to get to a single Dirac, and then it took a while how to get to a bulk insulating single Dirac with Fermi level in that. So in the Weyl semimetal case, first we want to find a Weyl semimetal that has a fewer Fermi arcs, ideally a pair or even one. And that for that we need to break time reversal. So if you have let's say we have a single Fermi arc on the surface, then you could see that there is no backscattering. Even kinematically, it's impossible. So there would be a surface state that has no backscattering. It's fully chiral, right? So it's like quantum Hall in higher dimension type of thing. So you would have surface state that in the 3D TI, the surface state is it's protected against backscattering, but you have side scattering. But in a TR broken single Fermi arc surface states, you have no backscattering. And then if you can tune the Fermi level at the Weyl point so that the bulk carriers are zero, so that sort of thing would be fully dissipationless, right? So we have to realize such a thing, and that's one of the roadmaps. The other thing is how to induce superconductivity and realize exotic topological order parameters. So one can think that, okay, even if you take a pair of arc and then your superconductivity, the pairing amplitude goes to zero at this point. So it will also lead to interesting topological or non-topological exotic superconducting states. Then that has those stuff has its own thing. And then so this is about the surface, that a chiral single arc chiral topological surface state and Weyl semimetal has all these things, but then in the bulk you have the chiral Landau levels, right? So that's also dissipationless, but you need a magnetic field there. So all these things have potential. In principle, they have potential applications if you can realize those materials or tailor the present materials to those directions. And, so it will depend on how the materials development go.
So my question goes a bit beyond what Sandro said before. For superconductivity, you need attraction, and all this description about topology seems to be based on single electron physics, on complicated structures set by the crystal. So my question is, how do you will combine this semi-metal Weyl semi-metal physics with superconductivity? It seems that this match is not so easy to do, right?
There is theoretical work to do, but experimentally, I think before theory goes there, experimentally we can sort of get results. That doesn't answer your question. I guess you're asking theoretical.
Yeah, well, both actually. It is also this proximity effect actually. One approach, but are there other approaches? What type of pairing will that be actually?
From Aaron S-Way superconductor, you probably just gap out the Fermi. But Professor Hasan said, so you can add some interesting interaction into it and solve the problem self-consistently. And you ask what type of pairing is possible.
Yeah, and also bulk, like you could consider pairing within the Weyl cone and then inter-Weyl cone, and there are all sorts of terms you could consider. And one interesting thing about Weyl systems is that I think of all the topological systems we are working on, this would be probably the easiest channel to bring in longer range Coulomb interaction, because once we find a T breaking Weyl semimetal that already has interaction built in. In fact, the interaction is what created that topological state, the Weyl state, right? Because it's magnetically ordered. So then this is a natural platform to bring in topology and interaction together. And I think even theoretically that frontier is open.
Okay. Thank you very much. Thank you again for Professor Hasan for his wonderful talk. And thank you all for coming.